This is a very brief lecture about the Bourne-Haber cycle, which is at the tag end of Chapter 10. The Bourne-Haber cycle is a way to find the lattice energy. So you may remember from last semester that lattice energy refers to the strength with which ions are held together in a three-dimensional lattice structure. So the stronger the attraction between all of the ions, the higher the lattice energy will be. Well, lattice energy is not something that can be measured directly. So the Bourne-Haber cycle uses Hess's law, and just kind of a reminder, Hess's law is when you combine multiple other reactions that are not the reaction you necessarily want information about. But you combine these other reactions in such a way that when you add them together, the net reaction you get is the one you're interested in. So that's what the Bourne-Haber cycle does. And it helps to understand by looking at the picture on the right here. So here is an ionic crystal lattice. And lattice energy that we're talking about, in other words, the attraction between the individual ions in a 3D lattice, is represented by here, enthalpy of lattice, okay? And again, that can't be measured directly. So the Bourne-Haber cycle takes us through a series of steps, and we'll go over each one of them briefly, where you start with the individual neutral elements. So the metal would be, in the example I'm using, sodium, neutral sodium. The nonmetal in this case would be chlorine gas. Now, everything has to be in the gas phase for this cycle to continue. So we would dissociate, if it's a diatomic like chlorine, you have to dissociate it into the individual atoms. And the metal being a solid, to take it into the gas phase, you would have to sublime it. Metal would sublime directly from the solid to the gas phase. At that point, you would have the individual isolated ions, and then, of course, the metal gaseous atom would need to ionize. It would need to lose an electron, right, to become the sodium cation. And so that's the enthalpy of ionization. The chlorine, neutral chlorine atoms would have to gain an electron to become the ion, okay? And that's electron affinity, when you add an electron to an atom. Anyway, we will go through those steps, and you'll be expected to be able to do calculations using the Bourne-Haber cycle. The equation that we use to solve for lattice energy using the Bourne-Haber cycle is shown here at the bottom. So just to kind of so that you understand what all the symbols are, in this case they're using U for lattice energy. And again, the individual reactions that are used in a Hess's law kind of combination are subliming the neutral metal. BE is bond energy, so that's dissociating. If the nonmetal is a diatomic, you've got to dissociate it into the individual atoms. And the 1/2 factor is there because you only need one of the two chlorines in Cl2. Ionization energy, remember, is removing an electron from a metal to make the cation. And electron affinity is adding an electron to the nonmetal to make the anion. And then part of the cycle, and I don't think I mentioned this in the last image, is enthalpy of formation for the ionic compound. So it could be confusing. You may be asking, all right, what is the difference between lattice energy, U, and enthalpy of formation? We're making the same compound, right? Well, just to remind you, the lattice energy involves combining two ions to make an ionic three-dimensional lattice. Okay, so it's energy involved in that, which we're calling U in this picture. And enthalpy of formation and remember the definition, actually that's an important one to remember, is the energy involved in making a substance, 1 mole of a substance, in this case NaCl, from its elements in their standard state. So enthalpy of formation for sodium chloride would be the neutral sodium atom. It's a solid in its standard state. Chlorine is the diatomic in its standard state. Of course, we only, in order for this reaction to balance and to follow the rules for enthalpy of formation, that it's only for 1 mole of the product, we have to put a 1/2 in front of the chlorine. So that's enthalpy of formation. And you can see by this image that if you add all of these up, you're going to get the ionization energy. Let's look at an example, plugging in the actual numbers. So just to remind you, here's the original equation, and this is the form of the equation that I would likely provide for you on an exam. But just to rearrange it to solve for what we're interested in, that's lattice energy. You get this. So it's important that you understand what each of these terms are. So then solving for the lattice energy for sodium chloride, you simply have to look at all of the individual values. So enthalpy of sublimation, right up here, is 108 kilojoules. And 1/2 bond dissociation energy for chlorine is right here. And you're going to have to be careful with that because not all nonmetals are going to be diatomics to begin with. So just be cautious, do some practice worksheets with and without a diatomic so that you know how to handle them. Ionization energy for sodium. And that's 496. And then, let's see, electron affinity for chlorine to become the chloride anion is minus 349. And the, here we go. The enthalpy of formation for sodium chloride is minus 411. That's way up here. Okay, anyway, so you add all these together, minus 788 kilojoules. Watch units. Also, it's important to do some of these practice problems because every now and then a problem will almost kind of deliberately try to trick you by changing units of some of them from joules, some of them kilojoules. So just be careful and do some practice. So here's another sample problem, calcium fluoride. Now this is already a bit different because think about what we did before, sodium chloride. We only needed 1 chlorine ion in this formula. Here we need 2. So again, you're going to have to be careful with the coefficients that you use in solving this problem. So here are all the individual values, and let's remember the equation that we need to use. Okay, it hasn't been rearranged yet. Remember, we're solving for lattice energy, which is the U, and plugging in all the values they gave us. There's the enthalpy of formation, the enthalpy of sublimation. Now, the bond energy for dissociating a fluorine. Okay, so that's the energy involved in breaking this bond. But notice that we need both fluorines, right? We're talking about calcium fluoride. It has 2 fluorines. So we did not put a 1/2 in front of this bond energy because we want to use both the fluorine atoms that it produces. So that's the kind of thing I want you to be cautious of, okay? Ionization energy for calcium. And, calcium has a +2 charge, right? It's in group 2A. And so you need to remove 2 electrons. So you need 2 ionization energy. And that is what we're seeing. Here's the first ionization. Here's the second ionization energy. Electron affinity, you have 2 fluorine atoms, so you need to add an electron to each of those 2 fluorine atoms. Okay, and then you're gonna plug in all those numbers, and then you're gonna rearrange and solve for ionization energy. And that is it. So this is really not difficult, but a lot of little tricks that you need to get familiar with by working problems.